reduction of couplings.
As everybody else, I would like to thank the organizers. I think it's a great idea to bring all of us here to discuss physics, people from Balkan countries and not only, in the spirit of the initiative of Goran, I thought under this not very predictable, content title to tell you what I'm doing more or less in various things. Now that I have seen also the time that is involved to do that, I'm not very optimistic anymore. So I will try as much as possible to be explicit, and most probably I have to first describe a few things. So the main question that I'm working about since a very long time is that the standard model has so many parameters. And what is really even more frightening, at least for me, is that our best candidate for physics beyond the standard model has even much more. So it looks a little bit funny to me. And this is the reason that I try in many ways, me and my friends, to reduce the various parameters of the theory. So in the first part of the talk, I will tell you about the reduction of couplings more or less a la Zimmerman, applied in supersymmetric theories, which further aim to achieve finiteness at the unification scale in magnified theories like we described before. We will see that we find the relations between Yukawas and Yates couplings, and they're predictive. We have predicted the top quantum mass before the discovery, as some of you might remember. And well, still we are testing things, and we do a scan with the parameter space, and we try to give predictions for the Higgs mass. If you find such relations between gates and Yukawas, then you get suspicious that these relations order one might suggest that they have a common origin, and then naturally you are thinking that maybe there is behind the whole picture a theory in high dimensions. So in the next step, I try to unify all the interactions in higher dimensions, and you see the Yukawas and the Gates interactions in this unified manner. This is the Horberg's mountain scheme that Paolo was referring this morning, and Klaus was talking on a variation of that. And the last part is to say that the extra dimensions are fuzzy. So we used to play with this more as a curiosity, let's say. But recently there are such solutions in strings, this electric effect. So the whole thing that we were playing, it seems, can be embedded in string somehow. So anyway, here I have first of all what good does the supersymmetry and why it was introduced, that it takes care of the quadratic divergences. And something which is not really very well known is that it restricts also the Higgs sector. And this is a very simple example of what I have in mind, let's say, that you might have some relations at the classical level that could survive at the quantum level at the predicted. So, for instance, if you take the standard model with two Higgs doublets and try to build the supersymmetric standard model, in general you write that much of couplings, And then you will see that the supersymmetry somehow restricts on these couplings. And this classical, let's say, restriction among gives relations of this sort, and it's nice that the radiative corrections, they give some masses for the Higgs, which are not very high, and this is why people are speculating really that the mass of the Higgs is nearby. And maybe you can see here something in general, minimal supersymmetric standard model, let's say plot between the mass of the Higgs and the mass of the top, and then you can see that you don't go very high. So very naively, this is what I have in mind when I look for classical, let's say, reduction of couplings. I'm not sure how far this can go. Let me come first to the quantum reduction of couplings. And we can imagine a Vrnjačka theory, as you considered in the previous talk. And there, of course, you have various couplings. You have the Gates coupling, and then you have various let's say, couplings. But the whole thing goes also to the dimension of parameters that you have in supersymmetric theories. So if you want a relation between the couplings, which is renormalization group invariant, really you are looking for solutions of this partial differential equation. And if you remember, or if you open a book in partial differential equations, you see very fast in one of the first theorems is that you have to solve a set of ordinary differential equations. And this brings us very fast to the solid ground of the reduction equations that have been discussed for years in Zimmerman, and the rest. So these are the reduction equations you're after. You want the aim is to reduce all the couplings of the theory in favor of one coupling, and in particular, I will demand, in addition, that the theory eventually is finite. It seems that the most recent demand is to assume such a power series solution. And the impressive thing is that already at one loop, you can decide if this series is uniquely, if it is can be determined uniquely, just checking things at one loop. And the proof, it's worth going through even fast, in spite of the limited time that I have at my disposal. So, just to get an intuition of how things work. So you write general beta functions for various things, and the proof goes by induction. You assume that you have uniquely determined the coefficients here up to something like R, and then you would like to determine the next coefficient. So you put everything together in the reduction equations, and what you get is something like that. So you want to determine this is uniquely, you have to guarantee that this is uniquely defined. And here you have guys which are known by assumption. And here you have a matrix which, as you see here, it involves only one loop quantities plus R, which runs in the natural numbers and the relation. So we go back to high school physics, and in order to have really to determine uniquely this type, all we have to guarantee is to guarantee that the determinant is different from 0. And you write a small program about that, and we do it. So let me skip few things that are not necessary, and I go to n equal 1 against the units, trying applying one way or the other. Let me remind you that if you write the most general superpotential, just opposite of what you do in ordinary theories, where you introduce wave function normalization, mass constant normalization, constant coupling normalization, constant in supersymmetry. This is something that you all know or you all heard of. There is a very strong non-normalization theorem which guarantees that all these constants are related among themselves, and there is only one infinity for each field that you have to take care of. Also, since it is very important for what I will be discussing, I flash for you how the beta function of the Gates coupling looks like. So here, because the quadratic azimuth of the group of the graphene-unified groups that you want, and here are the indices of the representation. So if you take the next step that I want to take, and you want not only to get rid of quadratic divergences, but to get rid also of all divergences, you have at one loop to give it the Gates group to choose also the representation of them of the fields, of the superfields of the theory. Next, also it's worth flashing how the beta function of the Yukawas looks like. So this is how you define the beta function for the Yukawas, and you see that they are proportional to the coupling itself, and here is the anomalous dimension which is related with the wave function normalization, and it has this form. So already you see here, if I want to demand at one loop that also I have finiteness of these guys, then I have already a relation between Gates and Yukawa couplings. This is nice because this is what I was looking for, and after these calculations, one can see that this is preserved even in two loops. So given some highly non-trivial calculations, here you can see that the Gates coupling beta function of two loops, it has the same term which was appearing in one loop Gates function, and also this which was appearing in the anomalous dimension. Similarly, in the anomalous dimension of two loop, you have again this, and here you see the anomalous dimension. Let me not discuss about this loops. So up to two loops, you can go in this simple way. You can just let's say choose the couplings in such a way that you can have finiteness to two loops. Of course, you would like to do much better than that. And there is a theorem which guarantees that, and based on this theorem, we wrote a model a long time ago. We have some other models that are meanwhile, and I will tell you about that. But I think it's the right moment to tell you why I like finite unification, because if I don't tell you, I will have a question. So I have to remind you that not only Dirac, but also other founders of the quantum field theory, they were not comfortable. They didn't feel comfortable about the fact of the appearance of divergences. So phrases like that are well known. In the recent years, of course, we have a more relaxed attitude, and we have even developed sort of intuition that the fact that we see divergences means that nearby there is a new physics cutoff. Of course, we were always worrying about quadratic divergences, because this means that one scale is related very drastically from another, and this is really the reason that the supersymmetry was introduced in the first place. However, in this spirit that somehow divergences means new physics, if you have unified all your interactions, naturally your theory should be finite. And I think this is not only me who says that, but this is the idea also behind the strings and the non-commutative geometers. And the only real difference is that I try to do it in the simplest framework, while the other schemes, of course, they include gravity. And the history, of course, of physics tells us that some things, new things might work, but in the simplest framework. Anyway, having this in mind, one can try n equal 4, and we know for every gauge group you have finite theories to all orders. And this was an impressive result, a very strong number of theorem. People who remember in early 80s, I mean, it was a big excitement about the fact that n equal 4 were finite. Of course, nobody tried to do real physics with n equal 4, and I did not try either. Then you can try n equal 2, which again has a very strong non-normalization theorem. From the point of view that it gets contributions only of one loop, so you have one loop, you put your stuff in, and then you can guarantee 2 all loops. But if you do that, the generic problem that you find, so this is, well, it looks like the beta function in that case. The generic problem, and let me not go in some big now because of lack of time, is every time you would like, let's say in region 5, if you want the 10 and the 5 bar, you have to live also with the 5 and 10 bar and things like that. So you have a whole mirror world anyway. So before you find a clever way how to get rid of the mirror world, you cannot go very far with this. So I have to concentrate really to n equal 1, and this is the best bet, as we said, for physics beyond the standard model. So I am in n equal 1 case. I have the general superpotential I told you before. The beta function that we discussed before tells you this, and you can, it's not a very difficult exercise. It has been done a long time ago by this guys asking with an anomaly cancellation to do a classification of all the groups and the corresponding representations that could satisfy these conditions. And the next requirement, as we already said, is to guarantee the vanishing of the anomalous dimensions. So you can see various things that the masses are not restricted, and you cannot apply these rules to the standard model because a U1, for instance, cannot satisfy, let's say, this condition because this will be vanishing, and you have to add guys which are positive and things like that. So you have to put supersymmetry breaking in the game by soft terms. As I already said, and I flashed the relevant transparency for you, one loop for finiteness guarantees two-loop finiteness. And then some brave guys, they continue and they try to see what happens in higher loops. And you can see that this can be guaranteed, but this does not, and so on. But you can imagine that this is not the way to go on. So far, what we have is that at one loop we have relations between the Yukawas and gauge couplings, and this guarantee the vanishing of the Yukawa beta function. So the theorem I was referring to is due to these guys, and what they said is, okay, assume the one loop finiteness conditions, but in addition, this relation which is given between Yukawa and gauge coupling, let it the linear normalization group vary. So now that we have a small experience, as I told you this matrix, that's why I told you this matrix, you have an intuition that you look really for solutions between Yukawa and gauge couplings that they satisfy this condition, and to guarantee that the determinant is non-zero, you have just to assume or to look to impose discrete symmetries and so on, that the solutions are not isolated are isolated and non-degenerated and so on. So from one point of view, in the way I describe it, it looks that the whole thing is not a big theorem. It's just a simple consequence of the Zimmermann's reduction, but it's not really like that. It's has much more than that, and let me tell you a few words about it, because this is the real reason why you cannot apply it in non-supersymmetric theories, which for my taste I would apply the finiteness also in non-supersymmetric theories. So in the massless supersymmetric theories, N-1, they have this well-known R symmetry, and here I have how the transformation properties of the various fields. You can write down the level current of this R current, and we know all here and know the first normalization theorem, the ordinary quantum theory, that the axial currents, they get contribution only at one group. On the other hand, Ferrara and Zoupanos with the superconformal group, they noticed that if you do R transformations and supersymmetry transformations and translations, all that closes in supersymmetry, so they form a supermultiplet, and in fact they form a vector supermultiplet. And these guys, they found that the anomalies of these currents, the relevant currents, they form also a supermultiplet. This time it's a chiral supermultiplet. And you see that every term has the beta function in front of that. And you see already the problem that there is a question if quantization is compatible with supersymmetry. Because this guy takes corrections only at one loop, and all the rest take two loops. So it was a challenge for some time, which I didn't follow at that time. Now I read from papers and so on, and discussions. And the point is the following. At the classical level, you have one R current. But at the quantum level, you cannot really have, they're not the same guys. So the two currents, one which is responsible for the Adler-Bardeen in the case of the axial R current, and the guy who sits in this supermultiplet are different at the quantum level. Nevertheless, and this is the big thing of Siebold and the rest, still they remember at the quantum level their classical origin in a way. And here there is a relation which is a normalization scheme independent practically. And here is the one loop Adler-Bardeen anomaly, and here are the beta functions and so on. So now, given this relation, you can go through the assumptions of the theorem, and you can prove finiteness order by order perturbation theory. So I wanted to say that it's not a simple thing; it's a big thing. Okay, let me only say one word about the finiteness of supersymmetry breaking terms, just to have an idea. So if these are the terms in the superpotential, in the supersymmetry breaking, you have corresponding couplings, and the first relation is that the H here has this relation with the U-kappa couplings and the Gaugino mass. And this is the other relation between the scalar masses and the Gaugino. And that can be relaxed, and I don't want to, for phenomenological reasons, this relation leads to problems. And there is a sum rule which can be satisfied to two loops and even to all orders, and this is something that we use. So with all that, let me tell you a model we have constructed some time ago, and this was examined also by other guys, but at the level of one look finiteness. Actually, if I remember well, some of these guys, they had some parametric solutions that explicitly violated the theorem I just said before. So you have an SU5, you have 3 families, you have a 24 that can break the gate symmetry, and instead of 5 and 5 bar, you have 4 of them. This is the cost really, but you have mass parameters and you can hide things, and eventually all the model building freedom you use it to approach the minimal supersymmetric standard model. So what we did is we wrote the superpotential, but we impose the appropriate discrete symmetries. By the way, you don't have even to impose discrete symmetries in this case, because in supersymmetry, if you don't put a coupling, it does not appear radiatively because of the normalization here. And then what you do is you calculate the beta functions. Of course, this model was taken from this big list, so from the beginning it's guaranteed that the one loop is vanishing, and you have to calculate the rest of 5 minutes. And again, so you put all that in the reduction equations and you find for solutions which are of the form that can be guaranteed, but they hold to all of this measure theory, and these are the kind of solutions that they guarantee the uniqueness of the coefficients, as I told you in the beginning. And then you go and you look you calculate the anomalous dimensions, and you find that the same kind of relations that you found before also give vanishing of the anomalous dimensions. So you satisfy all the requirements to have at hand one all-loop finite theory. So what you do then is you break the theory and you do some standard stuff here, which is better really do not have time to describe because it's a little bit dirty. So when you break the theory, you have a natural theory. Then after that, the theory runs. You can't satisfy the theory anymore the finiteness conditions. And it's very nice at this point to remind you all this hierarchy of constraints that we put in eigenvalue theories. Some of them they were reminded just before in the previous talk. So nowadays what you do is, this guy of course is well determined, and sine squared theta also well determined. You assume that the 3 lines they meet and you have a prediction for them. Strong, and depending from your theory, you say it's a good or a bad theory. Next, you put bottom down, you cover unification, the type of Zoupanos you have, and then you find such a window as a prediction for the top quark mass. For the SO10 that, as we had before, you put everything with the same multiplet, you find such a window, and we have also a relation of this sort. But what is nice in our case is that we have everything. Gate, stop, bottom, tau unification. We could be wrong all the way, but we were not, actually. So these are the models that we have. This is the first model before the discovery of the top quark. This was after, and okay, you can say always after you can do things like that. But the interesting thing is that nowadays the top quark mass, usually the theoreticians are putting the predictions, but here somehow we have that the fact that the top quark mass from the experimental side comes closer to us. So what we are doing now is that we scan, I cannot discuss now, we have a comfortable parameter space which we scan very carefully, just to show my collaborators in this business, and I can show you in a better diagram how the predictions from the Higgs look like. I don't care about the parameter. And okay, this is how it goes, and the spectrum looks like that. These are typical predictions, and I think I should not flash more than one transparency for the rest two. So what I had in mind to talk about, in addition, just is well, there's collaboration meeting here. I would like that you know what we are doing, and maybe build up new collaborations. This was the idea of Goran and the others. So we have seen all these nice relations between Gates and Rukawa, so you try to go to a unified theory, and we have models of the type of E8 in 10 dimensions that you try to reduce, and you bring things down to interesting GATs like E6 and SO10 and things like that. And unfortunately, I don't have the time, and I don't even dare to do that. And the last thing, but the most interesting things are based on these phases, which are the kind of nearly Keller posets, manifolds that even Klaus Berlin was mentioning this morning. So in principle, there is a discussion of how all this could be embedded in strings. And the last thing, which again I will not really dare to explain, is that we assume that the extra dimensions are a fuzzy manifold, and this is, before it was curiosity, now if you come from the string side, is the electric solution of Myers, which comes at Steinegger is with us now, and we try to embed the whole scheme in strings. And I think I will stop with that and show you only one flash. Transparency, which unfortunately I cannot find anymore. It's here. And this is about the Corfu school. And maybe the discussion session, I will tell you a little bit more. And I think it's a very good school of 22 days. And you should try to send your students. And I will try my best to provide some scholarships. Sorry for the...
Any questions for Mark? If not,